are our plate models as good as they will ever be, or is there room for improvement, and what direction are we meant to be moving on, or what should we be thinking about? And last year at the GSG at 50 meeting, I shared a talk with Dave McCarthy and Mark Allen, and we talked about how far plate tectonics has come in 60 years or so, and how we've gone from these somewhat simplistic reconstructions, and even before that from hand-drawn sketches, to very sophisticated models that actually show you almost like a time machine. It's almost like, I've heard somebody refer to this as like a Google Earth with a time slider, right, where you can see very closely spaced snapshots in time that allow you to analyze and to look at plate motion in more detail than ever before. And the truth is that compared to the 1960s and even before that, when plate reconstructions were at first just used to illustrate the notion of continental mobility, now we use plate models for a lot of things, and we expect a lot from them. Maybe the one thing that comes most often to people is that we use them as a framework to put other data into context, to get an idea in our head about how an area may have evolved over time, to help us interpret regional data or the evolution of a particular part of the world. And in doing that, we've greatly increased the complexity of plate models. And it was interesting when earlier Luigi was talking about analog models, and he was telling us how, depending on the resolution that you're interested in, you may build your model from different materials. Whereas with plate models, we don't do that. And in fact, over the last couple decades, our drive has been very much into integrating information and having our plate models illustrate everything from the very, very big scale plate motion to, something like the development of a part of a margin, and how does the margin deform as a continent breaks apart. So in a certain way, I started thinking about plate models, or about this type of plate models, as almost like as a visualization tool more than a predictive tool, because what we're doing is we're integrating lots of information. It makes it easier for us to get our head around what's going on in a certain period of time. So it's not surprising that we've gone from kind of the one single reconstruction, like this one for the Atlantic, to now, if you look at any area of the world and you look for plate models, most of the time you have lots of answers, lots of solutions. And that's because different authors, different groups use different types of data, or give more weight to certain types of data over others. They integrate different understandings, so you end up with different solutions. And they're partly due to slightly different modeling techniques, but mostly due to different input data sets. And often, particularly with students, I don't think it's exclusive to students, people say, well, which one do I choose? And I think in my abstract, I actually wrote something like, how do you choose a good plate model? What is a good plate model? Does that even exist? And the truth is that, well, when you're presented with something like this, in reality, it's not one right one and five wrong. They'll all be right to an extent. And really what makes a good plate model might be more dependent on what you want to use it for. So in this case, if what you're really interested in is the timing of connection between the South Atlantic and the Southern Ocean, say, so across the Falkland Plateau, well, you're going to get different answers depending on what you use. So it definitely can have an impact. Now, so that's part of what we use plate models for, is a sort of framework, is a big picture. But we also more and more rely on plate models for constraints for other models and other simulations. So we're kind of, in geoscience, we depend quite a lot on models and on simulations. And sometimes we've started using observations from plate models to inform other things, like it might be, I don't know, paleoclimate simulation, or even to obtain clues about some of the most fundamental questions in our science, for which is very hard to keep moving forward. And the one that always comes back to me is plate driving forces, and it's still very much partly an unanswered question. And we started looking at plate models and what plate models predict to try to further our understanding of, okay, what forces actually influence plate motion. And so for a bit of the talk now, I'm going to come back to this later, and to what makes a good plate model? How do we keep moving forward? But I'm going to talk a little bit about an example of a case where an observation from a plate model actually went on to building a new hypothesis that gained a lot of momentum and a lot of popularity even. And this is what I introduced a couple of years ago, and that is the Plume-push hypothesis. So in around 2010, somebody noticed that the Indian plate was behaving a little bit strange, moving very, very fast, like the Indian plate put the foot down on the accelerator, and spreading increased very dramatically at the time that the reunion plume was arriving in the Indian Ocean. So this hypothesis was born that two things were linked, they coincide in space and time. So the plume arrives and it's observed that India speeds up, and also it was observed that Africa slows down. And so it was, this hypothesis came about that the two things were linked. And after these first couple of papers in 2010, 2011 were published, this hypothesis gained a lot of momentum. There's been a huge amount of literature that attributes various different things to plume-push, to a pushing force introduced by a plume as it reaches the base of the lithosphere. And it's been invoked to explain things like plate boundary reorganizations, the initiation of subduction, changes in the dynamics of plate motion across big plate circuits. So it's really gained a lot of momentum. And a few years ago, me together with a couple of colleagues, we were talking about this, and particularly with Graham Eagles, we had both either ourselves or with students worked in this part of the world. So I had done a lot of work in South Atlantic. He had done a lot of work in the Indian Ocean and down in Antarctica. And we thought, well, maybe it's worth revisiting this and actually having a look at whether in our models, we can also see this sort of strange behavior of India and Africa when the plume arrives. So the diagram there on your right is a velocity triangle. So if you've never seen one before, the length of the lines tells you something about the speed of plate motion. So the longer the line, the faster the spreading rate between the two plates connected by the line. And then the direction of the line tells you about the direction that the plates are moving. So sometimes people ask, oh, but if you're interested in looking at the effect of a plume in the Indian Ocean, why are you looking so far? Why are you looking at the South Atlantic? And the reason why is because if you change any sides of this triangle, the whole triangle changes. What that means is that if you indeed have a pushing force associated with the plume, and that pushing force increases the speed of India and decreases the speed of Africa, it's going to affect also the other plates in the circuit, the other plates that share boundaries with Africa and with India. That's why we look at the entire circuit. And what we're looking for are those strange behaviors at around the time that the reunion plume arrives. And something that we did here that wasn't done before is that, so each of these white boxes is a model and a plate model, and they are all produced on the basis of the same type of input data and using the same modeling method, using something called Nankival inversion. And that's quite important. If you want to think of it, if you want to think of an analogy, it's like if you're measuring the speed of cars going down the road, you probably want to measure them all using the same instrument. Because if you use a variety of instruments, then you will never know what differences are down to the cars themselves and what differences are down to your different instruments being calibrated differently. So we're using all models that are comparable. In this little schematic on the right, so we have a plume that is coming under the Africa-India boundary. And so these red arrows are representing the push force introduced by the plume. So you can see that their direction on the Indian side is the same as the motion of India. So it's going to tend to speed that plate up, but it opposes the motion of Africa. So it should slow Africa down. And that's what we're looking for. We're looking for a speed up on the Indian side and a slow down on the South Atlantic side. And indeed, we can see a very big spike. The spreading rates, both in the India, Antarctica, and India, Africa ridges increase greatly at the time that the plume arrives. So we find exactly the same as others found before. The thing is, we also find spreading spikes everywhere else. And this is different to what was found before, where they were seeing a slowdown in the South Atlantic. And after we published this work, actually, I was working in the North Atlantic, which is very far from the Indian Ocean and from the plume. And I can see the spreading rate spike in the North Atlantic ridge as well. And Graham was working in the Eastern Pacific, and it's the same story. So we've gone from a starting hypothesis that said that, there's this pulse of super fast spreading, and it might be associated with the mantle plume, to us finding that actually this pulse affects seemingly every single spreading ridge in the planet. And because the planet's not getting any bigger, then we can only conclude that, well, then what, every subduction zone is also, subduction is also speeding up everywhere for a very, very short period of time. And then it goes back to normal, like nothing happened. That to us just seems like a bleep. I don't think anybody would look at that and think, oh, hold on, what kind of geodynamic mechanism could I use to explain this? That the answer is there isn't one, particularly because of what I just said, that it's not just that everything accelerates, it's the fact that as quick as it accelerates, it just disappears again, it leaves no trace behind. And because we're dealing with spreading rates, and spreading rates is just our distance in time, right? So if either our distances or our times are wrong, then they will create an artifact like this. And the easiest explanation is that the time scale is a little bit wrong around this time. So that the magnetic chrones that we use for plate modeling here and the ages that we assign to those magnetic chrones are a little bit wrong. So they're giving us this spike. It's just an artifact, it's not real. If we get rid of it and we look at the long-term trends in spreading rates across these spreading centers, they're quite predictable. There's nothing funny about them. There's nothing that requires a plume to explain them. Yes, on the Indian side, things are getting a bit faster, and on the African side, they're getting a bit slower. But you can explain that very easily simply by looking at the types of plate boundaries that you have in the circuit and how they evolve through time. This type of behavior, which is gradual, is much more consistent with how we understand plate tectonics to work. It's wrong with me being a geodynamicist to say, oh, plate tectonics is boring. It's not boring. It's just quite, it's just not these very unexpected, very sudden, strange events are very, very rare. So gradual change is much more common. And so you might be thinking, well, that's fine. But then in this case, the fact that somebody suggested a hypothesis from a plate observation, that the reason why the hypothesis was ill-founded had nothing really to do with the plate model itself. It was to do with the fact that the time scale is wrong, like might need correcting in that period of time. And that is partly true, but it's also partly not, because there is something to be said about the plate model. Now, if originally the authors that first proposed Plume-push had observed these spikes across all spreading centers, I doubt they would have proposed Plume-push. What they saw was that the Indian side had a spike and the South Atlantic side didn't. And the reason why they saw that is because their model for the South Atlantic lacked resolution. And again, going back to what Luigi was saying with analog models and what I was saying earlier about what makes a good plate model and choosing a plate model depending on what you need it for. In their plate model, they had no data between C25 and C29, which is this red box here. And the shaded box is the time when the plume arrives and the time when those sudden strange events happen. So effectively, their model is lacking resolution in exactly the time period where you need the resolution to observe what is happening there. And this is not me pointing the finger and saying, oh, you silly people, you chose the wrong plate model. Not at all. Missing these specific fronts, I would say probably 95% of models for the South Atlantic missed them, including my own. And the reason is very simple, and is that there are so many magnetic picks for the South Atlantic that are already published that most of us don't go back to the raw data and interpret raw data again, because we don't need to. We just go to published compilations. It's only in times like this where you notice that, oh, hold on, it coincides exactly with the time I need, that you have to go back to the raw data and stare at it and think, how can I find somebody that actually even knows how to interpret this? Which is the situation I found myself in a couple of years ago. And let me tell you, I had to learn how to interpret it, and it involves a lot of squinting at the screen. It's not easy. So going back to leaving that example aside for a second and going back to what I was talking about earlier about how, when we are trying to choose a plate model, we need to think quite hard about what we need it for. I think plate models today can almost be divided into two groups. On one hand, you have plate models as visualization tools. I can never say that word. As an illustration of knowledge. They take a lot of information, a lot of data at various spatial and temporal scales, a lot of geological interpretations, and they collate them into a nice picture or series of pictures that you can look at and that can inform you. So in that way, they're more just an illustration of our understanding. And then on the other hand, you have plate models that you want to actually use as independent frameworks. And in that case, you really don't want to have a model based on lots of geological interpretation. You almost want to go the opposite way. If you want to study plate motion, plate driving forces, you want a model with as little uncertainty as possible. And perhaps the way to achieve that is to ask ourselves, well, for this particular part of the world, for this particular range of times, what is the bare minimum I need to build a robust plate model with quantified uncertainties? There will be like a completely independent picture that then I can use to put whatever other information I have into context. To bring that home for more of you perhaps is to kind of like saying, going back to the Atlantic, if you're interested in, say, mapping the continent ocean boundary along South America and Africa, ideally, what you should do that from is a plate model that does not use interpretations of that feature as an input. Because if you use one of these, for example, one of these models here, they all, as a starting point, one of the things they use is where do they think that the continent stops and the ocean begins. So if you use one of them to map the COB, you're just going to map whatever the authors used in the first place. And that's why I had in my title this sort of going around in circles that can be a little bit counterproductive. And there's lots of examples of that. Plume-push is another one where we use a model observation to derive a new hypothesis and then ongo numerical modelers to model the magnitude of forces generated at the head of plumes from that hypothesis. And then that goes back to plate modelers that every time they see a plume, they go, oh, I need to take this into account because the numerical modeler said, this is how much, this is the kind of forces that it introduces and so on. So it's being mindful of those loops. Now, I don't think there's anything wrong with having these more like sort of illustrative models and models that compile lots of information. They're extremely useful. But because I'm quite interested in those questions surrounding plate motion and plate driving forces, I've been spending a lot of time thinking about how can we improve our models for that purpose? How can we produce models with very low uncertainties where essentially we have a very, very strong foundation to then go on and generate other models from having a strong starting point. And I think maybe we need to go right back to basics. And regardless of whether you're producing a model where you want to integrate lots of data or you're producing a model where you want to keep things very simple and abstracted from geological interpretation, there's one thing that they all share, and is that they need to work under terrestrial physics. They need to be consistent with the rules of geodynamics. And it's something we've been talking about a lot in the team since I joined NAFTEX is how can we build this sort of geodynamic rulebook that allows us to, for any plate model that we have, actually have almost like a checklist, a go-to guide to pick out things that that plate model may be predicting that are simply not possible on Earth. And here is the more complicated loop or circle of them all. And is that to write such a book, the only way we can write a book telling us things like how fast can plates move or how slow, or what motions, what rotations they can do, or how can plate boundaries evolve. The only thing we have to go on to write such a thing are plate models. But then I just said that this rulebook would be really used to validate plate models. So I'm going around in circles, and that would really get me nowhere. So are we trapped here? I don't think we are. I think what we need to do is remember that the present is the key to the past, or in plate modeling, the recent past is the key to deep time. There are workflows and there are ways, and the Indian plume and our models for that part of the world are an example. All of the models that we use for that part of the world only use seafloor spreading data, which is a type of data that has very, very low uncertainties, is very well understood. Every rotation pole in those models has confidence estimates. So effectively, the way we're building those models, we're putting numbers in and getting numbers out. And numbers may be scary if you don't like maths and physics, but actually they can be very reassuring. There's very little geological interpretation that has gone into those models, and therefore there's very little uncertainty. So if we, for a moment, put our focus in building some very robust models for this recent past, for the time where we have oceans, when we have oceanic lithosphere, so up to about 200 million years, then maybe we can use what we learn from those models. We can observe things from those models. We can observe plate motion, observe plate behaviors, the dynamics of plate motion, and then apply those things to deeper time. When we go further back in time, when we have very little to go on, it's very, very difficult to model plate motions, and it's a much more qualitative process. Maybe we can start writing the first chapter of that rule book using quantitative recent past plate models. So it can be sometimes a little controversial. I've had people like look at me like, what's she talking about? When I say, sometimes it's good to not put all the data that you have into models, just leave some of it aside, see what is the best basis to build them on, not try to integrate everything, but it can be very useful. I really think it can be very useful in moving us forward. So I think I just said most of these things. I forgot to advance my slide, but just to recap, what makes a good plate model, it's very dependent on what you will be used it for. And whilst models that compile a lot of data, a lot of information, give a really nice picture of how an area may have evolved, ultimately they're a best guess, and they should not be just taken at face value. And they certainly are less of a good basis to investigate certain fundamental aspects of geodynamics, where we need to stay as far away from uncertainty as possible. Instead, maybe we can use geodynamics more to our advantage and make sure that we're building models where plate boundaries are evolving in ways that we know plate boundaries to evolve, and where we don't have very strange events of super accelerations of plates that come and go very quickly. And before I forget, plumes aren't pushy. Perhaps we've proven a negative, and somebody said this to me a while back. Oh, all you've shown is that there is no record in plate models. There's nothing we can see that supports the notion that plumes introduce a push force. And that's true. We have proven a negative, but think about it, that is better than, Plume-push at the moment, the only evidence behind it was the Indian Ocean case. And there is nothing there. Yet we still see, even this year, last year, we continue to see publications that invoke Plume-push as a mechanism explaining events. And it's a hypothesis without evidence now. The evidence is gone. So maybe we've proved a negative, but still, until we find evidence to prove it, well, I think plumes are not pushing mechanisms. And I'll wrap up there, but as I said, I must give a shout out to Tectonica. So very, very quickly, for those of you that haven't heard yet, Tectonica will be a Diamond open access journal. It's launching very soon, meaning it's opening for submissions very soon. We've been working on it for over a year now. And the idea is to provide an alternative to traditional publishing models. So Tectonica will be free for everyone forever. It'll be free for authors to publish and free for readers to access. And it relies entirely on volunteers. And I won't go on here and tell you everything about it, because instead I will just tell you to check out the website, which is tectonica.online. You can read more about the journal there. You can read about our editorial team. We just appointed our first set of executive editors, and we are currently appointing associates as well. You can find ways to get involved. You can join our Slack workspace, which has over 170 people in it. You can follow us on social media. And if you're not keen on social media, you can use the register here link on the website, and then you'll get an email when we're open for submissions. You can also, I think, express your interest if you'd like to review for us, which would be awesome. You can dedicate your time to a free access journal. There's a button there that says make a submission. Don't make a submission. Nobody will review it. It's not quite open yet. I think we need to change that button. And last thing, sort of a first look for TSG attendees, because we haven't announced it yet, but we now have a little merch shop. So we have financial support from the University of Aberdeen. We're partnering with them to help us with the logistics and the infrastructure for Tectonica. But we've opened a merch shop, and the profits here will also go to the journal. So we hope that we have a healthy-ish financial status so that we can do more than publish the journal, and we can in the future do other things like run seminar series or maybe offer some small grants, or I don't know. So all profits from the shop are gonna go towards the journal in some form. So yeah, I think I'll leave it at that and take any questions if there are any about Tectonica or about the talk.